Hello again, everybody. This is Dr. Hammond for Phys 2510 Electromagnetic Waves. And this will be the last lecture that we have for this course, talking about class notes. And I'm just going to summarize some of the notation we have for electrodynamics in tensor notation. So we've talked a little bit about tensors before, we haven't talked so much about tensors before, but we've talked about Lorentz transformations and how that's a four-dimensional matrix. Now I'm going to expand this idea or extend this idea of Lorentz transformations for position, proper velocity, relativistic momentum, and I'm going to talk more about electromagnetic effects such as charge density and current density, as well as the potentials. So what we have is a scalar. The charge density is simply the charge divided by some volume. And the current density, of course, is this charge times charge density times some velocity. So we already know that before. We've learned that, many chapters ago, I guess even in electromagnetic theory. But now, as a relativistic effect, if the charges are moving, then this volume will have a Lorentz contraction, right? So in the dimension that it's moving in, we'll have this Lorentz factor. But of course, so say if it's moving in the x direction, then we have this Lorentz factor. But in the y and z dimension, we don't have this. So the volume just changes in one dimension, and so we just have to worry about gamma. We don't have to worry about the other two dimensions. So there's a length contraction just in that dimension, and so we get a contraction of this volume. So now the charge, of course, doesn't change because we still have whatever charges we've put in. It turns out charges are invariant, just like mass is invariant. So whatever charges we have in this volume is still Q, but now this volume is going to be smaller. And so the relativistic charge density is going to be gamma times this rest charge density, or the proper charge density, I should say. And also, when we look at current density, what we're going to have is, we can think of this two ways. Either we have this current density is going to be rho times u, so just as we had here, but we know that rho is gamma rho naught. So we can either think of this as rho naught gamma u or gamma rho naught u. Either way, it leads to the same thing, that what we have is that the 4 vector for current can be represented by this rho naught by the proper charge density times the proper velocity. And so where if you think about the 0th element, what we have is rho naught times this contravariant element of eta naught, and so rho naught gamma c or rho c. So this contravariant 4 vector of the current density is c times rho and jx, jy, gz. And so what we get is that we had thought that we had, a 3-dimensional vector for current density and a scalar for charge density. Now we can lump them all together so that the scalar is the 0th element, and then we have this 3 vector is the x, y, z elements. Now we can look at the continuity equation, and so we have the divergence of J, so divergence of this current density is the rate of change of the charge density. So it's a amount of charge that's flowing out of this volume. So what does this look like in each dimension? Well, the divergence of J is, of course, the derivative of Jx with respect to x, the derivative of Jy with respect to y, and the derivative of Jz with respect to z. Or you can write this in a more compact notation. It's a sum over I of the derivative of J with respect to the ith position element. And the 0th element of this contravariant vector will be the rate of change of the charge density is equal to 1 over c times the rate of change of this current with respect to time. And so that gives us dj by dx naught. And so if we can put this all together to get that the derivative of this contravariant current with respect to position, this 4-vector position, is equal to 0. And so what that means, this is the 4-dimensional divergence of J. And so basically the continuity equation is saying we have 3 dimensions here and we end up having a 4th dimension here. So we can put them all together into one vector and say we can take this divergence of this 4-vector and we find that the current density of a 4-vector is divergenceless, which is pretty neat. And so basically this is the continuity equation, basically saying that if we sum up over all spatial dimensions and time, then that derivative is going to be 0. Okay, so that's how we work for current. For those of you paying attention, in the last assignment, this is how you solve for part B in question 2, I believe it is. And also we're going to do this for 4 vectors, so this is part A for that question 2 in the last assignment. So what we have is this 4-vector in the potential is going to be, we have, as you would expect, we have the vector potential, so that's going to take up x, y, and z elements, and the 0th element is going to be a scalar, and so that's just going to be v divided by c, so that the units work out. So this scalar potential divided by c. So now if we're being in the Lorentz gauge, we look at the divergence of the vector potential is negative 1 over c squared, and the rate of change of this scalar potential. But we can do the exact same thing here, just like what we did here for the continuity equation. And this basically, if you recognize this is just minus 1 over, or the 1 over c squared, this is just a continuity equation for the potential. And so in the Lorentz gauge, you see where this is going, that the divergence of this 4-vector is actually 0. So if we take all spatial dimensions and the time dimension, this thing has no divergence in space and time. So it's basically a continuity equation. This Lorentz gauge is basically a continuity equation for our potentials, which I thought was fairly interesting. And also remember from before how we had that the D'Alembert of the scalar potential is equal to negative rho over epsilon naught, and we had this, the D'Alembert of the vector potential is negative mu naught j, and so the vector potential is dependent on the current density and the scalar potential is dependent on the charge density. Well, we can now lump all these things together just like we did, and we see that the D'Alembert of this contravariant 4-vector potential is negative mu naught times this contravariant current 4-vector. So I thought that's nice and tidy. It kind of summarizes all these things that we've been seeing with conservation of charge and things like that. And we can write them into nice, tidy, compact notation. And so I like that this has a very nice symmetry. It's a very elegant way of looking at these equations and looking at this physics. And so this is one of the powers of the Lorentz gauge when using it for electricity and magnetism. All right, and I'm going to finish off with Maxwell stress tensor. So we didn't really use this in this course. This was part of chapter 8, and which we skipped over. I have not seen Maxwell stress tensor used in anything besides very specific examples. And in fact, Feynman's paradox is, I think, the only time I've ever seen Maxwell stress tensor, even in graduate problems. It's basically only introduced in terms of that. It's probably used in general relativity and things like that when we're looking at, like, charged, massive objects or something like that. But unless if you're going to do, graduate studies in general relativity and cosmology, I have never really seen a purpose of Maxwell stress tensor. But I'm just going to talk about it here for completion, for completeness sake, and on the possible chance that you do go into grad studies and are interested in this stuff, just so you have a passing familiarity with this, so that people bring up Maxwell stress tensor and you don't say you've never heard of that before. Now you can say that you have. So Maxwell stress tensor, all it is it's a tensor that relays the off-diagonal elements and the diagonal elements of an electric field and the off-diagonal elements and diagonal elements of a magnetic field to give you this tensor. So this is Maxwell stress tensor, and what does it mean? So you're going to have txx elements, txy, txz, tyx, tyy, tyz. This will be a 3x3 matrix. And what this is saying is that for, say, txx, you have 1/2 epsilon naught ex squared minus ey squared minus ez squared plus 1/2 mu naught bx squared minus by squared minus bz squared. And so this is the diagonal elements, and the off-diagonal elements will look like txy. So you have epsilon naught exy plus 1/mu naught bx by. So if you think about what's going on in the diagonal elements, it's x's, x's acting on x's, y's acting on y's, and z acting on z's. And so this is like a pressure. So this is like, txx is like x acting on x. And so that's kind of like, that's like a pressure. Whereas the off-diagonal elements are called shears. So it's like x acting on y. So you push on y and something happens or you push in x and something happens in y. So here is you push in x and something happens in x. This is just kind of what you're used to. You push you have a force in x and it accelerates in x. Whereas this is a shear, so you would be pushing some object in x and it would be moving in the y direction or something like that. And so a tensor just tells you how this is going to be working. And so it's a little bit more complicated mathematically, but basically it's just a 3x3 matrix that tells you how to describe these forces. So the reason why it's kind of important is that in what we were just discussing is we had, from the continuity equation, we had the divergence of J is going to be the rate of change of the charge density, and we had the divergence of the Poynting vector is the rate of change of the energy stored in the field. So this is energy conservation. Now, so something that I hadn't talked about before, but what we have is we want to have conservation of momentum, but in these two cases we have this element on the right is a scalar and this is energy, so this is again a scalar. So of course you could actually put this into tensor notation as well if you want it to be more compact. But now what we have is for momentum is actually a vector. So that means that we can't have the divergence of a vector equaling a vector, because the divergence of a vector is of course a scalar. And so now basically you could see that this is going to be the case that this is going to have to be a tensor, because we have that the rate of change of some vector is going to have to be the divergence of not a vector, but the divergence of a tensor. And so the divergence of a tensor gives us a vector. And so that's where Maxwell stress tensor comes in, is it gives us the conservation of momentum. Okay, so that summarizes everything that you need to know about electromagnetic waves. I hope you guys have been following closely. Thank you very much for following me as we've gone online. I know that this has really changed how these courses go. I really liked being able to interact with everybody and be able to ask you guys questions and have you guys ask me questions too. But unfortunately, that is it just seemed like it wasn't in the cards to end this semester. So I've been getting a lot of emails from people asking me questions, so please continue to do that. I am always happy to answer your questions. Yeah, please, if watch the, if you're at this point now, you've been watching these videos, so hopefully they've been helping you I preferred to do it this way rather than have live video because it seemed like that would be really difficult to make sure that everybody could connect at the right time and that everybody had a good enough internet connection. Whereas this way you can watch it at your leisure. So hopefully it's worked out okay for you guys. But I guess this is the end of these lecture notes. So the next one on Thursday will be, I will just be available for you to ask me questions about the poster, which will be due in about 3 weeks or so, which will be making up your final exam. So don't start that too late because you'll be having other exams coming up soon. So you might as well start it soon and be able to ask me questions and work with me on it as you develop it. All right, well, thank you very much. And this is basically the end of the course. So I hope you've enjoyed these lecture notes. And I guess until the fall, take care.